Yeah, let's get started. Okay, first of all, any questions for logistics? No? Okay. Okay, so we're still early yet, so I'll probably wait for a little bit for our homework one. Okay. Yeah. Let's review what we covered in our last lecture. So in our last lecture, we finished talking about how do we measure information, right? So basically, we introduced the concept of entropy. Okay, so one thing to remember here is that entropy is not a definition, right? So we derive it from our 4 axioms. Okay, so that's very important to understand the basic idea of entropy. So here's a review of the probability space, right? So we did it, we introduced it 2 lectures ago, right? So here we consider a random event or random variable, which is x. And then, so small x basically means the realization or the outcomes of a random experiment, right? And then, so we have the concept of this sample space, so or the event space, right? So it's written as the calligraphic x, okay? And then we introduce the probability mass function again. So here we consider discrete event, right? So we do not consider, so basically it means that the capital X is a discrete random variable, okay? So we're gonna focus that for a while, right? If you think about it, it kind of makes sense, right? So because a lot of information we're transmitting or we're compressing today, they are discrete, right? For example, if X is a file, right? So that obviously that's all 0 and 1s, right? So basically, and even if it's analog, right? So like a voice or video or whatever, right? So basically we can, we sample that, quantize it, convert that to a digital signal, and then we process it, right? So consider X is a discrete random variable, seems pretty good for now, okay? And then we denote h of x as the measure of information or a measure of uncertainty, right? Because in our class, we think information and uncertainty, they are equivalent. Information is uncertainty, okay? All right, and from here, we assume that h of x is a function of px, or a function of the probability mass function, right? And remember that, so now we just introduced this notation h of x here, right? We didn't tell you what hx is, okay? And in order to derive h of x or entropy, then we need the following 4 axioms, right? So I'm not going to repeat that. So we introduced that like 2 lectures ago. Okay, probably the most important one here is axiom 1, right? Because that gives you the basic uncertainty of information, right? So basically, if we consider the probability, we have 2 outcomes only, and each has a probability of half, then the entropy is 1, okay? And then the other very important axiom is axiom 4, probably, right? It's a grouping property, so this is not extremely obvious. You need to think a little bit, right? So basically, if we group, outcomes 1, 2, then the entropy equals to the entropy after grouping plus the probability times, the entropy within the group. Okay, so that's very important. Okay, and using that, we can derive 2 important lemmas. So the first lemma is that h of n and m equals to hn plus hm, right? Remember, small h basically means this, right? So here's the notation, okay? And from here, we can see, so, if inside is a multiplication, then outside is addition. So we immediately think about it's probably a log function, right? Log function satisfies that. And it turns out that by using lemma 1 and our 4 axioms, it turns out that log function is the only function satisfying this property, and also all the 4 axioms, obviously, right? Therefore, we can show that h of n equals to log 2 base 2n, right? The reason we have base 2 here is because we have axiom 1, right? If it's not axiom 1, then we can use other base as well, okay? And by using all of those, then we can derive our entropy is given by this formula. Is we have minus here, and then our probability times log 2 the probability mass function, okay? And because the probability is less than 1, and we have a minus here, therefore, so entropy should be what? Bigger than 0, or bigger than or equal to 0, okay? Which kind of makes sense, right? So what does the negative uncertainty means, right? So here, entropy is always bigger than or equal to 0. Okay, and then for the unit of entropy, so we have a few units here. So we just mentioned bits here. So that's the one we use most commonly. Okay. And so this coming from the axiom 1, right? So if we assume axiom 1 here, then we have to use bits. Okay. Otherwise, we can use natural bits or nets. Okay. So that's a base e, right? So if the log is based on the natural number e, right, then we can use the net. Okay, so both of them are used normally. Okay, bits is just more popular, I guess. Okay, and later on we're gonna see that. So this bit is called information bit, right? So which is almost the same as the bits, we normally use in practice, right? But there's a slight difference. So we're going to talk about the difference now. Okay, so let's see. So today. Yeah, let me double check if the recording still working. Oh, cannot do that. Yeah, have to. Okay, then let's see the recording. Okay, still going. Okay, great. Okay, let me do this again. All right. Okay, so EEL6532. So today is our lecture number 4. Okay, so we have a few topics for today. Yeah, do you mind if close the door? Thank you. Yeah, probably today and our next lecture. So I'm going to cover the following topics, right? So we'll see how far we can go. So the first is that we're going to give you one example of entropy to see some properties of entropy. Right, and then we're going to introduce you another very important information theoretic concept. It's called self-information. Okay, and then we're going to talk about the properties of entropy. We kind of mentioned at least one of them already, right? Which is the entropy is always bigger than or equal to 0. Okay, and then after that, we're going to talk about another kind of related but also important concept in information theory. So it's called the joint thing. Okay, so we're talking about the joint entropy and the joint self-information and the joint entropy. Right? By joint, basically we consider if there's more than one random variables. Okay, let's see whether there's anything changed or not. Okay, joint self-information and joint entropy. Okay, and after that, so because now we're considering more than one random variables, right? So if we consider more than one random variables in probability, then we consider what? The joint distribution, right? With kind of the joint entropy. And then we consider conditional distribution, right? Therefore, we have also this concept here. So we have the conditional self-information and the conditional entropy, okay? So it's kind of very natural extension. Conditional self-information and conditional entropy. Entropy. And then we introduce another important property here. It's called chain rule. So which is very similar to the chain rule in probability by using the Bayes rule. Okay, and we're gonna see how far we can go today. So those are our agenda. Okay, let's see the first one. Okay, so examples of entropy. Okay, so as usual, we're just considering the most example and the simplest property, in our class, right? Which is what? Flip a coin. Okay. So now we're, since we're considering this, this random variables, right? So we just call that, let's consider this, right? So if we assume a random variable x here, right? I assume that, so a equals to 1 with a probability p. So WP here means with probability, okay? And 0, obviously, with probability 1 minus p. Okay, consider this kind of random variable. Okay, so obviously it's called binary, right? Therefore, the entropy we're going to compute is called the binary entropy function. Okay, very good. So do you know what does that called? So did you remember what is this called? This kind of random variable? Yeah, what? Go ahead. Exactly, Bernoulli distribution, right? So we can see. So this is extremely important, right? In our class, almost all the topics in the discrete random variable, so we're going to assume a Bernoulli distribution, or Bernoulli is just a binary, right? So if you consider a bit more, so it's called what? Binomial distribution, right? We just focus on this kind of two distributions. So those distributions are pretty magic. So we're going to see they are very representative. Bernoulli distribution, we call that a Bernoulli distribution with a probability p. Okay, so that's a probability that x equals to 1. Okay, very good. Okay, so now let's compute the entropy here, right? Using this distribution, right? Let's recall that. So the entropy function h of x equals to what? Minus, so we sum over all the x in our set of x, right? So px log base 2 px, right? So this is the definition of entropy. Okay, so normally or very often, so we can put the minus sign inside and write this, okay? So obviously either of them is fine, but just, sometimes we prefer, this way, right? If we have a minus sign in front, we'll think, okay, that might be a negative number, right? Which is not, so. Okay, so now let's compute it. So in this case, we have only, the summation now is only 2 terms, right? So which is 0 and 1, okay? We just plug that in. So when x is 1, so it's p times log base 2 1 over p, and plus the other one is 1 minus p, log 2 1 over 1 minus p. Okay, so that's basically the formula of the binary entropy function. Okay, any questions? Okay, great. Yeah, that should be simple enough. And then we denote that as h2p. So this is a notation. Okay, so so this notation and this notation are different, right? So h of x is just a general notation for entropy, right? But this, we have a small 2 here, and then we consider that as a function of p only, right? So this is a binary entropy function, right? So this is basically, so binary entropy function means basically this. Okay, so now let's see the value of it, right? So whether that makes sense or whether that is interesting or not, right? So we consider some very extreme value here, right? So the first one is that, let's see the first case, when p equals to half, right? So that's the case we consider previously, right? If we toss a coin, if the coin is a fair, then with half probability is 1, half probability is 0, right? Then what would be the entropy? Okay, so let's compute it. So in this case, h2p, so that equals to half log 2 half plus the same, right? So 1 minus half is still half here, half log 2 1 over half. Okay, what does that equal to? 1, right? Because, so this log 2, 1 over 2, so that's what?
Should that be just 2?
Oh, yeah, so, there's a mistake here. So 1 over p, right? So, yes, log 2, then the first one is half, and the second is half. So basically we have a 1. Okay, very good. And so we call that 1 bit here because we use base 2. Okay, so that should be no problem. Let's see the second one. The second example we're going to consider is that, so we're going to consider something extreme, right? So what if p is 1, right? So with the probability 1 is a 1, with the probability 0 is a 0. It means what? Certain, almost certain, right? In probability language, we call that almost certain. We don't call that certain. Why is that? Right? Why in probability language we always call it almost sure, right? We don't call it sure. There is the concept of sure.
Is it because there is another outcome even if the probability of it happening is 0?
Very good. Exactly. Right? So now we still have two outcomes. So the other outcome 0 happens with probability 0, but it's a legit outcome. Does that make sense? So although it will never happen, but still it is a possibility. It just cannot happen. Right? Yeah, it actually is pretty important. So let's say if we learn measure theory, it basically means, so this has a measure 0. Okay, measure 0 is still, there's something going on, but just cannot happen. Okay. Yeah, probably we're gonna touch a little bit in the future, in the later part of the class. Yeah, so yeah, now it feels silly, right? But it's not. Okay. Well, where are we? Yeah, so now let's compute it, right? So basically, in this case, so let's compute it. H2P, that equals to 1 times log 2, 1 plus 1 minus 1 log over 1 minus 1. Okay? So here, the first one is pretty obvious, so that's 0, right? What is the second one? What does that equal to? So 1 minus 1 equals 0, and log 1 over 0 is log of infinity. Right? Log infinity, if we put that downstairs, it's also 0. Right? So basically 0 over 0, then we can now compute it. Then what do? We use the L'Hopital rule. Right? We just use L'Hopital rule. Yeah, you can compute at home, so it's pretty easy. So that also equal to 0. Okay? So, yeah, which is kind of, if you don't want to use L'Hopital rule, it's kind of intuitive, right? Because we have 0, multiply a log 0, right? And the log is, when we're using L'Hopital rule, basically, we have to, track the trends here, right? So something goes to 0, something goes to infinity, right? Then, what's the value of it? It's a limit, right? So here you can see that, if this guy is a linear function, so that goes to 0, compared to the speed of this guy goes to what? Infinity, right? So basically you can see that this is much faster, right? So then it should be 0. But you should compute it still. Okay, and then the result is 0. Okay, so now let's see, does it make sense? It did, right? Because entropy 0 means that there's no uncertainty, which is true. We don't have any uncertainty, right? Because we know 1 happened with probability 1. Okay, so we're pretty sure about it, which is good. Okay, so now we have two extreme points, right? So here, probably you can also see that, right? So how about H2 0 here, right? So if P is 1, then it's 0, but what if it's 0? Yes?
Sorry, just a question on so we have, oh, never mind, I got it. I figured the math out.
Yeah, okay, great, then let's answer the question. So what if P is 0? It would be the same as P equals to 1, right? Because P equals 0 basically means that x equals to 1 cannot happen. We know that 0 must happen, right? So therefore, intuitively, that's equal to 0 as well, right? So now we have 3 important points for this distribution. So we know when, let's draw it, right? Here's P, here's H2P. So we know when P is 0, it equals to 0. We know when P is 1, it equals to 1, right? And we know when P is half, it equals to, when P is 1, it's also 0. When P is half, it is what? It's 1, right? Half. Okay, so now we know the function should be like increase and decrease, something like that, right? But we don't know exactly how to do that. So we're gonna see how we do that. So, but I'll tell you now. So it looks like this. It looks like this. Oh my God, it doesn't. Yeah, it should be symmetric, right? So, yeah, it will be a symmetric with the line of P equals to half. Okay. Okay, very good. Okay, we're gonna prove why the curve look like this later. Okay, but from this curve, so did you learn anything about convex function, concave function before? Right. So it's convex or concave, or neither? Yes, it's a concave function. But we're going to cover that later. So, okay, so from this figure, so we can see there's some very important property here, right? So one thing that is very obvious is that the maximum value of this function is basically happen when p is half. Okay, so we know h of 2p, that's always less than or equal to 1. Okay, and 1 equals to when p is half. Okay, so that is very important. Does that make sense, by the way? It did, right? Because when p is half, then we really have no idea whether we should lean towards to 1 or 0, right? So that's the maximum amount of uncertainty that should achieve the maximum amount of entropy, okay? And this also equals to, so if we go back here, so basically you can see that, so basically it means that all the values here are identical. There are 2, right? And the coefficient in front, add them together, it'll be 1, right? Therefore, so this also equals to log 2 the cardinality of our set X. Okay, so in this case, the cardinality of our set X is basically 2, right? So that's equals to log 2, so that's equals to 1. Okay? So that's very important. And let's emphasize here is that, okay, so H2P is maximized at p equals to half. Okay, so that's very important, right? So this is a very basic, very simple example of entropy. Okay, any questions so far? Yes.
So the 2 in H2 denotes that it's binary entropy. There's 2 outcomes, right?
Yes.
Okay.
Exactly. But normally we only go up here, right? So later on you're going to see that this is a very special function. We're going to use that all the time, right? We don't use 3, 4, 5. We just use 2. Okay. Okay, so now let's see the second concept, so which is self-information. Okay, again, so now we'll consider a general X. It's capital X, so the distribution of that again is still P, okay? And so we consider discrete random variable here. Okay, then the self-information is defined as follows, okay? So let's say that if we observe X, okay, that's the outcome, okay? So the self-information is defined as follows. Self-information. So this is defined as this guy, I of small x, okay? So this is the outcome, right? So that is minus log 2 px, or log 2 1 over px. Okay? So what's the meaning of it? Right? Consider the definition of entropy here. So this is the definition of entropy, right? Or this, okay? And the self-information is nothing but only this part, right? If you look at that, right? So this is self-information, okay? Yeah, sum in front, then we got an entropy, right? But this is only a self-information for small x, for each outcome. So what does that mean? Yes?
You sample something, if the probability is really low, it means that you're very, you gain a lot of information when you get it, and then it's the opposite.
Very good, yeah, that's true. Yeah, but that's only for each x, right? So that's the key here, okay? So it means the uncertainty for each small x, for each outcome. Does that make sense? So that's the physical meaning of it. Okay, so basically, the meaning of that is, so it measures the uncertainty of one outcome, small x. Okay, so for each outcome, we have a I of x, right? It's a function, okay? So now if we write inside like big X, or the random variable here, then we can see that this small I of capital X is a random variable, right? So this is a random variable, okay? Therefore, because the definition of self-information, so we can basically write entropy as a function of self-information, right? So what is that? Right, so can we write entropy h of x, right, as a function of self-information? So we know that equals to this, right? So then that is basically px times I small x, right? And if we see this kind of function, so what does this operation called? What is this operation called?
Weighted sum.
Say again?
Weighted sum.
Weighted sum, yes. And another term in probability?
Expectation.
Exactly, expectation, right? So that's the expectation. We can write expectation of I capital X, then that's basically the entropy, okay? Okay, so from this meaning, so yeah, we can have a more clear view of entropy, right? Because so Ix means the uncertainty of one outcome, right? And the entropy is an expectation of this, right? So basically, entropy is kind of like the measures of the entropy or the uncertainty of all outcomes, right? Or the average uncertainty of all outcomes. Does that make sense? Okay, so let's repeat it. So Ix is the measure uncertainty of one outcome, and this guy measures uncertainty of all outcomes. Okay, very good. Yeah, so this is another kind of meaning for entropy. Any questions? Yes.
So I of small x is the uncertainty of one outcome.
Yes.
And then I of the discrete random variable x
Mm-hmm.
is a function of all the individual outcomes.
Yeah, this guy.
Yeah.
Yeah, normally we don't say that. Yeah, x is a random variable, right? So we just say, okay, then, therefore this guy is still a measure of one outcome, or cannot really say that, right? Because it's random. You know what I mean, right? So yeah, we just replace the small x by capital X, meaning that is a random variable. Random variable basically means it can take, as long as the probability is not zero, so it can take values for all of them, right? But we don't call it a measure of all outcomes. No, that's entropy. Does that make sense?
Yeah.
Yeah, so I think there's a clear meaning of I small x, clear meaning of entropy. This is just the, the intermediate step. Okay, yeah, let's don't go that far too. Yeah, but it's a very good question. We should, but later on you're going to see that it's a kind of a tool, right? We need that to define all other information theoretic concept later on. Yeah, that's very good. Okay, so then let's talk about the properties of entropy. Okay, the first property is what we mentioned before. So entropy is bigger than or equal to 0. Okay, can we prove that? Yeah, it should be relatively straightforward, right? So let's do that. So we know that entropy is an expectation of self-information, right? And if we can show each self-information is bigger than 0, then entropy is bigger than 0, right? Because it's just weighted sum of each of them, right? And we know that I of small x, so that equals to this guy, right? We know that is definitely bigger than or equal to 0, right? Because inside is always bigger than or equal to 1, right? So yeah, this is because 1 less than px less than 1, right? Therefore, we're done. Okay, the proof is very straightforward. Okay, and another important property of entropy is also what we mentioned before. So h of x is less than or equal to log 2 of the cardinality of the set. Okay, we didn't prove that before, so we kind of verified that before using the binary entropy function, right? So, yeah, let's, so the equality sign holds. Right, so for in information theory, so we always this equal sign has to be kind of precise, okay? So the equal sign is super important, and later on you're going to see that, right? So we need to really understand when the equality sign can hold, okay? So the equality sign holds if and only if. So it's a double direction, if and only if, sufficient and necessary condition, right? Can you tell me? So basically, we need to pick a distribution to make this equality sign hold, right? So what kind of distribution do you think? Uniform, right, uniform. Like before, right, it's half and half, then that equals to log 2, right? So it turns out that it's the only distribution can make this happen, so it's sufficient and necessary. Okay, so we're going to prove that later, so we're not going to do that now. So we're going to prove that later, okay? Prove it later. Okay. Okay, great. So yeah, that's the first topic. Okay, the second one, so then, as we mentioned before, so we're going to consider more general case, right? So now we just focus on one random variable, right? So now we're going to focus on more than one random variable, okay? The second one is the joint self-information. And joint entropy. So because now we have this, understanding that the entropy is an expectation of self-information, right? So from now on, we'll just, introduce all the concept by introducing self-information, and then do the expectation, then we get whatever, okay? Okay, joint entropy. Okay, so now instead of one random variable, now consider more than one random variable, right? The simplest case for more than one random variable is two random variable, okay? So now we consider discrete random variables. Okay, so now we consider x and y instead of only x, right? Clearly, the distribution of that is what? It's px and y, right? So this is a PMF. Okay, and we'll consider there's a set of x, and then there's a set of y. So calligraphic x, and this is calligraphic y. Okay, so now let's see. So is that straightforward or easy to define what we have learned before for just one random variable? That's straightforward. Or is there anything special for two random variables? No, right? Why is no? It's because we can combine them, right? So we can just, consider this as a one big random variable. Okay, just more outcomes, right? Then the problem is done, right? It's not so difficult. So there's no big difference. Consider this as a single vector valued random variable, okay? And then we can define whatever we want before, right? But there is something special that we do need to consider, right? Because now, we do have like two random variables, right? And x and y can kind of depend on each other, right? There will be something interesting to observe, right? So now let's define. So, but definition, again, will be exactly the same as before, right? For the definition of joint self-information, it's nothing but equals to log 1 over pxy, right? So that's exact same before. And then the joint entropy which again is exactly the same as before. So hxy instead of just hx. So that's equal to the expectation of I, capital X, capital Y here. Okay. And then, so that equals to, we can write it out, right? So now we have two random variables. So we have double summation here. We have x in x. and y in y, right? And then we have pxy log 2 1 over pxy. Okay, very good. And then we can take, this minus sign out, right? So yeah, we can write in that way if you like. Okay, so that's the definition of the joint entropy. Okay, so there's no difference compared to before. And because there's no difference, so we can also say that all the concept for entropy will hold for joint entropy as well, right? Therefore, so the joint entropy is bigger than or equal to 0. Okay, so entropy before will hold. Okay, so now let's see something special, right? So now, since we do have two random variables, and then we can introduce the concept of the conditional self-information and the conditional entropy. Okay, so let's see that conditional self-information and the conditional entropy. Okay, so yeah, again, so we consider the distribution as before. Okay, and so now we need to introduce you the conditional PMF. Okay, so that's the base rule. Hopefully still remember it. So the probability of x given y, so that equals the probability of x and y divided by the probability of y. Okay, so that's Bayes' rule in probability. Okay, any question on that? Right, the meaning of this is basically, so given the fact that y is happening, then what is the probability that x is happening? Okay, and how to compute that is, we use the probability of x and y and divide it by the probability of y. Okay, that makes sense? Okay, great. So this is a joint distribution, and from there, so we basically, then we're going to use everything we have defined before to define the conditional self-information and the conditional entropy, right? Using this probability distribution, this conditional probability distribution, instead of px or pxy. Okay, so that's basically So let's write it down. So given the, given the realization. So realization here basically means small x and y. It's an outcome. Okay, so it also means outcome. So given realizations or outcomes x and y, and then we define the conditional self-information as follows: ix given y, so that equals to log 2 1 over px given y. That's it, right? So there's nothing new there, okay? But the meaning of that is kind of interesting, right? So this means the uncertainty of x given y is happening, okay? So for example, let's say if x and y are perfectly dependent. Let's say if x equals to 1 and y equals to 1, x equals 0, and then y equals 0, right? We only have these two outcomes, okay? And then basically means that if I tell you x is 1, then y has to be 1, right? There's no uncertainty, okay? So that's basically the meaning of it, right? So this is the uncertainty of outcome x given the outcome y. Okay. Okay, great. And then by using that, we can define the conditional entropy, right? This is a bit tricky here. Okay, let's see how we can do that. Okay, so now let's see, given the realization y, and then we can compute the expectation of I. Okay, so here it's a bit tricky, right? Let's say we know y is happening, right? So given small y, so that's the outcome, right? And then we could compute the expectation of the random variable x. Okay, so we're going to write, and if we do this expectation, we know that's kind of some entropy, right? But it's kind of tricky. So it's entropy of x given capital Y is y, right? Because we know small y is happening. Does that make sense? Okay. Then if we write it out, then we can see that equals to x in capital X, and then p x given y log 1 over px given y. Okay, so that's basically this, right? It's very important to, so this is what we're computing. H entropy of x given y equals to small y. Okay, then can we, so clearly, so if we write that in this way, so can we do a weighted sum over y of this guy? We can, right? So now it's basically, okay, we know small y is happening, right? And then we do expectation or weighted sum of this self-information and to get this, okay? So how about we also do the expectation of this again over y? Does that make sense? Okay, so we do another averaging here. So basically, what we're doing is as follows. So basically, what we're doing, what we're doing is that, so now instead of write a small y here, so we're going to write a capital Y here, which is a random variable. Okay, so then it basically means that, so now we're doing an expectation of y, on top of it. Okay, I'll now write that here, so you can put that here. Okay. Okay, so now let's manipulate it, right? So this here is that, so look at that. So we have a py here, and we have a px given y here. So we can put them together, right? This multiply that. So what are that equals to? So what are this multiply that equals to?
The probability of x and y.
Exactly, right? Bayes rule, right? So basically, here the product here is a probability of x and y. Okay, and then we can write down the summation. We have double summation here. So x in x, y in y. Okay, very good. And then we have a log to 1 over px given y. Okay, so now we can see that if you consider x and y, both of them are random variables, so this is just the probability of x and y, right? So this is nothing but, so a expectation of 1 log 2 1 over p x and y. That makes sense? Kind of weird, right? So we have a probability here, but what is inside the probability is a random variable, right? Here you can just consider this probability as a function, okay? It's a function of random variable, right? And then the expectation is basically we do that over this function. That makes sense? Kind of weird, yes.
I'm still confused. Like if we know the probability, so we know the okay. So if we know the probability of x and y, but I'm still confused. Like why do we need the interest rate for what kind of things? Like we know the probability already.
Yeah, we know but yeah, come on. So we know the probability, right? But we don't know what exactly will happen, unless some probability is 1, right? So if I toss a coin, so I know, okay, with half is a head, half is a tail. So you know what will happen? No, you don't. Right? So you know the distribution, but it doesn't mean you know what will happen. Right? You only know what is going on after you do the experiment and see what is going on, then you know. Right? Yeah, this is a very good question. Right? Knowing the probability doesn't mean you know what will happen. Right? That makes sense? Yes?
How does the last line work?
Last line work. From here to here?
Yeah.
Okay, great. Yeah, so this is a definition. Yeah, this is a very good question. So this is pretty confusing, I think. So from here to here is the definition of expectation. So expectation is over x and y. Right? So if you consider this is a function, and then we do expectation of this function, so this is the formula you're going to do it. Right? Yeah, I think we just need to understand in this way. It's pure math. Okay? Yeah, I know it's kind of confusing because now we have a p x given y, but here x and y are random variable. It's a probability, and then inside is a random variable. Kind of weird.
So it's not p x given y?
It is. It's p x given y.
At the front.
Yeah, front. Yeah, it's here, right? Yeah, but so basically, if we write expectation, so we just absorb that in the expectation. Okay. So yeah, this definition. So this basically is the definition of expectation.
So the reason that like at the top it's p
Mhm.
x given y.
Mm-hmm. From here.
Because it is y given small y.
Yes.
And
Yeah.
then-
So here we use that. Let's see. So this guy equals to this guy multiply this guy, right? So here we use the Bayes rule, this formula, right? So this multiply that, then equals to pxy, right? And then we get pxy here. That makes sense? Make sense? Okay, great. All right, so actually, this kind of notation, we use that quite a bit in machine learning as well. Okay, so it's kind of expectation of a probability of some random variable. Okay, great. And then we call that, so now we're pretty much done for this concept. So we call this h of x given y. Okay, so this is called conditional entropy. Okay? So here it's very important. When we write conditional entropy, so then the averaging or expectation has to be taken on p, x, and y, not this. Okay? So this is not called conditional entropy. So this is called conditional entropy. Average is on both x and y. So this is very confusing. Yeah, we just need to be careful on that. And so the reason I do in this way is that I'll let you know what is really going on. Right? Otherwise, if you see that, okay, y will have a pxy here, right? Not px given y, right? So px given y means this, okay? And then here we have to do the average on both x and y, okay? And the other thing is that, so clearly it's still entropy, right? Because we just use the definition of entropy here. So this is bigger than or equal to 0. Okay? Any questions? Yes?
Yeah, so we at the top we have the entropy of the random variable x given y is some specific value.
Yes.
And then at the bottom we have the entropy of the random variable x, so any possible value x can take for any possible value y can take.
Yes.
Okay.
It's still weird, but that's true.
Okay.
Yeah, so yeah, here, so h of x given y is like you don't know exactly which y is happening. Okay, but you do know something about y. So it's yeah, later on I think it will be more clear, but this definition is pretty weird. Yeah, so this is very clear, right? You know exactly, okay, why is happening. Okay, then what's the uncertainty of x, right? But here is that, okay, so we average all of them and then get this. Okay, but in practice, people usually think in this way, right? So people always think, okay, conditional entropy means that I know y, then what is uncertainty of x? Precisely, it's not that. But roughly speaking, it's more or less true. Okay. Yeah. Okay, so let's end for today. So we're going to continue to talk about conditional entropy next time.